Here we have a network or a graph, a weighted graph, and we want to find the shortest path from a single source to the other vertices. So a source is given, it can be any vertex, but usually in the test you are going to have node 1 as the source. And we want to find the shortest path from node 1 to all the other vertices. The algorithm that we use is called modified Dijkstra algorithm to find the shortest path. And it works for the graphs with negative weights, negativeCijs, or even if the graph is not a digraph, it is undirected graph, we can have, for example, here instead of this arc, directed graph, directed arc from 1 to 2. If it is not directed, I can show another arc like this, once going from 1 to 2, another time from 2 to 4. It means that if there is no direction, you can move in either direction. So you can convert to a digraph and use the same method. So even if we have a negative Cij here, the algorithm will work, but in this case there will be a condition. Like this one. In the previous case, you can see that here there is no cycle. It means that if I start from 3 and there is a negative arc here, or arc with a negative weight here, I cannot come back to 3 on a cycle. If I go from 3 out, then there's no way to come back to 3. So in this case, there is no problem for the negativeCijs. But in case that we can start, for example, in this case, from 2 and go around this cycle and come back to 2, it's okay if there is a cycle, but the cycle must have non-negative weight. It means that if I go around this cycle and the sum of theCijs gives us a negative value, then the algorithm will diverge. So imagine that all the conditions are valid. We have all positiveCijs, or in the case of negative Cij, there is no cycle with negative weight. How the algorithm works. We start with the initialization step like this. We say that source, we write here a table to show the vertices. For example, I said that source is 1. So from now, we don't need to reach to 1. We are already at 1. We want to see if I want to go from 1 to, for example, 4, what's going to be the cost or the distance from 1 to 4. If I go from 1 to 4, I may select this arc and that one, and the sum of these two ones becomes 2. Or I may go to 2 and then there's no way. So there's this way, or if I go to 3 and then 2 again, I cannot reach 4. So there's only one path from 1 to 4. That's going to be the shortest path from 1 to 4. From 1 to 2, we have two paths. They can go from 1 to 2 directly, or from 1 to 3 and then 3 to 2, or maybe 1 to 3, 3 to 4, and then 4 to 1. If we compare them, we can see that this is going to be the shortest path if I go from 1 to 3, 3 to 4, and then come to 2. So in case that we have 4 or 10 number of vertices or edges, so we can find all the possible paths and compare them. But usually we want to use the algorithm for a case that we have many vertices and arcs. Now how the algorithm starts, originally we say that to go from 1 to 1, so there is no cost for us. So we write this wi primes on the vertices to show the cost or the distance from source to that vertex. So from 1 to 1 there is no distance, w1 prime is 0. And when we want to start the algorithm, we don't know whether we can reach to vertex 2, 3, or 4 or not. So originally we say that, or we consider that they are not reachable for now unless we find the path from the source to that vertex. So in the initialization step, we give infinity for all w prime, but not for source. For the source, we give 0. And there's another thing here that we call scan eligible set. It means that we want to start from this vertex or this node and check if we can find the path from this to the adjacent or other vertices. So I want to start from 1 and scan the adjacent vertices. And if I can find the path, then I will modify this infinity to something else. Now, this is the initialization step. All wi prime infinity, w1 prime 0, scanable set 1. Now, in each iteration, we will do these things. So let's see iteration 1. So all the other iterations will be the same. In each iteration, we may modify something. If we modify something, we show here by red color. So these are something that we modified in this iteration. But how we do that? We select one of the vertices from a scan eligible set. You can select any of them. If we have more than one, we pick that and we remove it from the scan eligible set. And start to check whether we can modify any other wi primes based on this vertex or not. So 1 is selected. So here we can see that here I showed by this color. Then 1 is selected and I check the forward start, means that going out from 1 and reaching to the adjacent vertices. So if I go from 1 to 2, then the cost or the weight or the distance is going to be 4, which is better than that infinity. Then we modify this infinity to 4. Since I modified this W2 prime, then 2 is going to be added to the scan eligible set. And also in this table, we say that we are reaching 2 from 1, or 1 is the predecessor of 2. So we may modify this 1. It means that next time I may come from 3 to 2, then I'm going to cross this 1 out and write another value next to that. And at the same time, we saw that we can modify 3, because from 1 I can reach 3 by this cost 1, which is better than infinity. Then 3 also is modified in this step. We add 3 to the scan eligible set. And we are reaching 3 from 1. So we should write all these things in red to show that in this iteration we did these changes. Next iteration is going to be almost the same, but we are going to start with a scan eligible set that we found here. The final scan eligible set for this iteration is going to be the starting a scan eligible for the next iteration. So in the next iteration, we will see this 2 and 3. Now, in this iteration, we start with 2 and 3 as a scan eligible set. We can start from 2 or 3 and modify the forward star vertices. Here we pick 3 and we remove it. If I pick and remove 3, then the scan eligible set changes to only 2. If I can modify anything, I will add that vertex inside the or into the scan eligible set. So let's look at 3. So we picked 3. See also the color shows that this time we picked 3. From 3 we can go to 4 or 2. If I go from 3 to 2, up to this point the weight or the distance was 1. It should be added by the Cij, which is 4. Is it better than 4? No, it is the same. It means that it can be a multiple solution, but we don't modify in this case. How about the other vertex? Yes, we can reach 4 also from 3. In the previous step it was infinity, but now up to 3 we had the total weight or total cost 1. We can add another 1 here for this vertex. Then it becomes 2, better than infinity. Then we modify this infinity to 2. Which vertex or which W prime has been modified? Only W4 prime, or for the vertex 4. So we add 4 into the scan eligible set. And also we say that we are coming to 4 from 3. So the predecessor of 4 also is determined or modified. Now we reach 4 from 3. Now we go to the next iteration, starting with this 2 and 4 as scanageable set. Now we have 2 and 4 as a scanageable set. We can pick 2 or 4. Here I pick 4 and remove it from a scanageable set. Then still 2 is there. Now from 4, outgoing arc, we have only 1 and it goes to 2. If I go from 4 to 2 up to 4, we had the total cost 2 plus another 1 becomes 3, better than the previously determined weight 4. So we modify it to 3. Now, since W2 prime has been modified, we need to add 2 to the scanageable set. But 2 is already there, so it will not change. It remains the same. But what else we did? We found that we can come to 2 from 4 with a better or lower cost. So the predecessor of 2 is going to be 4. So for 2, we are coming from 4. So we cross out the previous value and write a new one. So this red values here, red colors 4 and 3 are those that we found or we modified in this iteration. Next iteration. We have a scanageable set equal to 2. We pick 2 and a scanageable set becomes empty. But we might be able to modify something. Then if we modify, similar to the first iteration, we picked 1, it became empty, but we modified something and we add them to the scanageable set. But in this case, we pick 2, it's empty, but from 2 there is no outgoing arc. We cannot modify anything. Then we cannot add anything to the scanageable set. Once the scanageable set becomes empty, it is the end of the algorithm, and we say that the algorithm stops here. Now, how to give the final solution if we have this? So let's see by the information that here we have. This P and Q that we kept the predecessor of the vertices, it says that we are coming from 4 to 2, then we need to keep this arc from 4 to 2. We are coming from 1 to 3, we need to keep this one. Here I change the color. And we are reaching 4 from 3. So we change the color of these 3 edges, then we will remove the others. It means that in the shortest path we have only this 3. Now this is the final step. We keep only these vertices, and also for Wi prime we keep the last value, the modified value. For example, here we had infinity for 3, then we don't need these values. We are going to just keep the last one. So here Wi primes are 0, 1, 2, and 3. So if I draw the graph, it shows the shortest path from 1 to 3 is this one. From 1 to 4 is this arc and also the other arc. But if I want to introduce a path, we usually say that we are showing by a sequence of vertices. For example, from 1 to 4, I need to go from 1 to 3 and then 3 to 4. So this is a path, and this is going to be shortest path from 1 to 4. And to 2, we can see that we need to go from 1 to 3, then 3 to 4, and then 4 to 2. This is the shortest path from 1 to 2. What is the total distance from 1 to 2? It is 3. It's already here. But also we used all these things, so we kept all the information in this tableau. Let's see how we can read this shortest path here. Now, we want to see what's going to be the shortest path from 1 to 2. From 1 to 2, so we start from 2 itself. Okay, we write 2 itself here, 2. What's the predecessor of 2? 4. So we need to write 4 before that. And the predecessor of 4 is 3, then 3 comes before the 4. And what's the predecessor of 3? It is 1. So this is the way that we show the path based on the values for predecessors of what we kept in this PQ table. Now let's see another example similar to this. We have 5 vertices in this case and a little bit more edges. We do the same step by step initialization step, all wi primes infinity, only w1 prime 0. A scanable set, the source. So the question says that source is 1. Start from 1 and find the shortest path for all the other vertices, so source is 1. So first step or iteration. In the first iteration, we pick 1 from a scanable set. It becomes empty. And let's see, from 1 that we already picked, we can reach 2 and 3. We can go to 2 by the cost 2, then we modify this infinity to 2, and we write the name of this vertex inside the scanable set. And also here in this part, we say that we are reaching 2 from 1. We are coming to 2 from 1, then we write this 1 here. PQ or the arc 1, 2 should be kept to the final answer. From 1, we can modify 3. To go from 1 to 3, the total cost is going to be 6, better than infinity. We modified, then 3 should be added to the scanable set. We need to give the predecessor of the 3. We are coming to 3 from 1 for now, but later we may change it. In next iteration, we have this 2 and 3 starting scanable set. We have 2 and 3 here. We can pick 2 or 3. In this case, I pick 2. I remove it from a scanable set. What remains inside? Only 3. Now, if we can modify anything from 2, we will add that one to a scanable set. So let's see, 2 is selected in this, or we picked 2. Now from 2, I can go to 3 or 5. If I go from 2 to 4, up to this point, we had total weight 2 plus another cost of this arc 5, 7, better than infinity. Then we modified this vertex 4. Then 4 comes inside the scanable set. 3 already was there. Okay, this 3 is already here. And we are coming to 4 from 2. We are coming to 4 from 2. We write this 2 here, coming 4 from 2. Can we modify 3 also? So let's see. From 2 to 3, up to 2, we had total cost 2 plus the cost of this arc 5. 5 is better than 6, so we modify it. Since we modified, we need to add 3 to the scanable set, but it is already there. Another thing, we need to change the predecessor of 3. We are coming from 2 to 3. Previous step, it was coming from 1 to 3. Now we are coming from 2 to 3. So these are all parts that should be modified in this iteration. Next step, 4 and 3 was the last scanable set in the previous iteration. We can pick 4 or 3. Here I picked 3. So we pick 3. From 3 we can go to 4 or 5. From 3 to 4 up to here we had total cost 5 plus another 1, 6 better than the previously determined 7. Then we modified 4. 4 must be added to the scanable set. But it was already there, so we don't need to do anything. 4 is there. But one more thing should be changed. Coming to 4, right now we are coming from 3. So coming to 4, we are not coming from 2 anymore, we are coming from 3. So we modify this one. Now check one more thing. From 3 we can modify 5. We can go to 5. From 3 to 5 up to here we had total cost 5 plus another 3, 8, better than infinity. Then 5 has been modified. We add 5 into the scanable set, and its predecessor is 3, so it's determined we are coming from 3 to 5. So right now we have passed from 1 to all the vertices, but we don't know whether they are all the shortest path or not. We should continue up until the scanner set becomes empty, and there is no way to modify them. Continue. Next step, we are going to have this 3 and 4 as a scanner set. 3 and 4, we pick 4 and 5. We can pick 4 or 5. Let's say we picked 4 and we removed it, then the scanner set becomes 5. Now from 4, we are at 4 outgoing arcs or forward star arc. We have only one from vertex 4 to vertex 5 with a cost 1. Up to 4 total cost was 5 plus this one is 7, better than 8, so we modified. We modified 5, we need to add 5 into the scanner set, but it's already there, so it remains there. We don't do any change in this step, but we change the predecessor of 5. We are coming from 4 to 5, so we change this 3 to 4. And that's it. Now the scanner set is only 5. We go to the next step. We pick 5 and remove it. The scanner is empty. From 5, there's no way to go out to another vertex to modify it. Then we are not able to modify anything to add to the scanner set. Then it remains empty, and is the final step. Now, based on this tableau here, we can give the shortest path from vertex 1 or the source to all the other vertices. For example, I show one of them if I want to go from 1 to 4. So we know that the total cost is going to be the 6, but what's the path with this minimum weight? So I want to reach 4, so I write 4 here and come to this table for the predecessors. I reach 4 from 3, then I need to write 3 here. And then we reach 3 from 2, then 2 comes before that. And we reach 2 from 1. So the shortest path is going to be 1, 2, 3, 4. Here also we need to keep 1, 2, we need to keep this one. This one also shows that here 1, 2 means I need to keep this one. 2, 3, we need to keep this vertex. 3 to 4, we will keep this one. And 4 to 5, this one. And we can remove the others and give the final answer. Now this is the remaining arcs, which is a tree, but different from the minimum spanning tree that later we will study. So this is shortest path from 1 to 2, shortest path from 1 to 3, shortest path from 1 to 4, and shortest path from 1 to 5. Here also you can see all these things. And in the next video, we will start with a problem like this. And we will say that, let's say BIs are the values for the nodes. It says that B1 is 1. We have 1 unit of commodity to supply. And we want to, for example, we want to find the shortest path from 1 to 5. Where is the source and where is the destination? We need to know these two. Imagine that destination is 5. Then I'm going to write B5 negative 1. We show demands by negative value, so supplies by positive. Others, they don't need anything and they are not supplying anything. So B2, all other BIs are going to be equal to 0. Now I can write all the constraints as linear programming. However, it's going to be integer programming, or xij's are going to be 0 or 1. But I will explain all these things in the next video, that we want to solve it by solver. First, we write the linear programming model. It's going to be a kind of transportation problem, but we will solve with a solver as a linear programming.